the B vector?
8, negative 4, 1.
It is
8, negative 4, 1.
8, negative 4, 8, negative 4, 1. And so when you do this, the first thing I told you that we need to break this into LU as a product of LU factorization. And then so we can fix one of the variables, either the L variables or the U variables, to be 1, just for simplicity. Sometimes we can fix them to any value. So we can fix them to ones, or we can fix them to another value. In most cases in an exam, I will tell you the values to fix. And so maybe I can still avoid what I didn't do last time and then just fix this 0. And this is now L21, and then 2, 0, and then L31, L32, and then 2. So I've fixed the elements of the L matrix. And then U is U11, U12, U13, 0, U22, U23, and then 0, 0, and then this is U33. I don't know last time what did we fix last time?
U.
Yeah, so I'm just doing differently. So it's okay. So if you are not sure about going through what we are doing step by step to get the values, then just do this product and get the product, that product matrix. So I now multiply this L, U is the same as what? Let us just multiply. So we multiply row by column. You recall how we normally multiply matrices, right? Is row by column. That gives us 2 U11, right? And then this by this column, I'll get what? That is L21, U11. And then this part by this, I'll get what? L31, and then U11. Is that okay? You can multiply the same way you want. If you want, you can just go row-wise or column-wise. So this and this, I'll get this is 2 U12. And this part with this, I'll get what? It is L21, U12, and then plus 2 U22. And then lastly, this with this, I'll have what? I'll have L31, U12, and then plus L32, and then U22. And then I go to the last one. So here I have 2, 1, 3, U13. And then here I have what is L21, U13, and then plus 2, U23. And then lastly, I have L31, U13, and then plus L32, U23, and then plus 2, U33. So this is what you have. And so since this matrix should be decomposing the first matrix, then we equate the two matrices. And recall when I started by looking at matrices equality, we said two matrices are equal if their corresponding elements are the same. That means you equate each element at each position. So we should have what? 2 U11 is the same as 2, right? Is it 2? Yeah. So that means what? That means that U11 is the same as 1. Then we proceed. 2 U12 is the same as 1. That means U12 is the same as a half. And then 2 U13 is the same as what? Can you confirm? Tell me these values. Is the same as 2. Meaning U13 is the same as 1. So do you still want me to proceed?
Yes.
We go to the second row. So equating, I have L21, U11 is the same as, can you tell me the value of A at row number 2, the first value in row number 2? In the matrix. So read to me the matrix values. Because I don't have to keep on scrolling, so it's is equal to 1. I don't want to keep moving up and moving down, and you have these values. And our U11 is 1. What does it mean? It means L21 is 1, right? Because our U11 is 1. And then moving forward, I don't know which one is easier. I can go to this is much easier. So here, L31 multiplied by U11, which is 1, will be the same as, what is this element at this point?
4.
Is 4. So this is equal to 4, meaning L31 is 4. Then next, so equating these values, if you just look keenly, you start with the values where the unknowns are less. So I started with this, knowing that I only have one unknown. Going along this, you know that you have U11, so you only have one unknown. Now going along this, I know L21. I know. Do I know U22 and U12? Do I know? Yeah, I know U12. So I know everything except U22. So meaning I only have one unknown. So I have L21 multiplied by U12 plus 2 U22 is the same as, what is the value?
-3.
-3. Now plug in the values. Our L21 is 1, U12 is 0.5, then plus U22, the same as -3. What does it mean? That our U22 is the same as, it's -3 minus a half, and then divided by 2. So -3 minus a half. A half is what? So this is -6/2, and then minus a half. That's -7/2. Divided by 2. That's -7/4, right? Just confirm that it is. You will confirm these values. No, but I think here I don't need to proceed. So this one, since once you get this much, it's just equating and solving for these values. If you go to the next, you know L21, you know U13, you can easily get U23. Once you get these values, here you know L31, you know U12, you know L32. No, we don't know. So we look at, but we know U21. So this is only unknown at this point. If you go here, you know L31, you know 13, you know L32, you only have one unknown remaining. So these ones, you can do them easily. So assuming somebody got the values, you have here L, U, then X is the same as your B here, right? Then it means you start by let UX is the same as Y. You know that if you multiply a matrix by vector, you get what? You get a vector. And so you solve the system, Ly is the same as B. And L being an upper triangular matrix, because so you will have L has which components? 2, 0, 0. Can you try to see the values of L that we got? L21, what is L21? L21 is
1.
L21 is 1, and then 2, 0, and then L31. Do you have it?
4.
Is 4. L32. No, assuming let me just put here star, assuming we don't have it, but you can get it. So this multiplied by Y1, Y2, Y3 will give us what? B. But our B is what? 8, -4, 1. So that is 8, -4, and then 1. And so when you have a triangular matrix, solving the system, you don't struggle. If you have an L, then you solve by forward substitution. If you have a u, you solve by back substitution. So you just directly get the value. So from here, according to this line, it means 2u1 is the same as negative 8, meaning y1 is the same as what? Negative 4. And once you get this, now you plug in. This is y1, so it's y1 plus 2, y2 is the same as negative 4. I'm just writing them down, but if you want, you can just go directly. We got our y1 is 4, so I have negative 4 plus 2y2 is the same as negative 4. That means y2 is 0, right? Is it so? Can you confirm that y2 is 0?
Yes.
Yeah. Then if y2 is 0, it means 4y1 and then plus 2y3 is the same as 1. But y1 is minus 4. So that is minus 8. So it means y3 is the same as 9 over 2, right? Is that okay?
Yes.
Yeah, and so having found y, and now remember that we said that now our ux is the same as y. And so our u is our matrix now u11, u12, u13. And then this is 0, 0. The same way you have these values. Multiplied by x1, x2, x3 is the same as the y values, which you got here negative 4, 0, and 9 over 2. And then you do the same thing we did after Gaussian elimination. You are now doing back substitution. Start from this, get x3, x2, and x1. Is that okay? Is that clear? The one who asked.
It's clear.
Okay. So I know maybe what was confusing might have been the way we were solving LU, getting L and U, because I was trying to go the direct way so that you get these values sequentially as you keep on multiplying. If that is not working, don't worry. Just go step by step. Just multiply L and U with the unknowns, form the big matrix, and start equating the corresponding elements. And so I told you that if you just do it keenly, then you see that these values will just automatically come out. Just look at the rows which gives you one unknown at a time. Don't start with this where you have 3 unknowns. Then you get confused because there will be so many unknowns. So start with questions where you solve one unknown, and as you get that unknown, then it helps you solve the second unknown. Any other question? So I want to look at the second set of, or the second class of methods for solving systems of linear equation. And these methods are basically the ones mostly implemented into solving systems. Why? Because one, they are they require very less memory when you are using, even when you are programming. Then they only store very few values than the direct methods. And so these methods, they start with an initial condition, just an initial guess. And then you iteratively increase that guess until you convert it to a solution. That's how they start. And just guess an initial value. Then from the initial value, you try to improve it until you convert it to solutions. So you form sequences of xn. So you form x1, x2, x3. So you arrive at a solution if this sequence converges to a value x. And that point of convergence becomes the solution. So basically you have to keep in mind what you looked at, the sequences, and when do you say the sequence is convergent. If it does not converge, then it means you don't have a solution because the sequence diverges. So that's what happens. And so we can just write a few things at least. So we can say iterative methods or schemes for solving the system AX is equal to B start with an initial guess. Say, for example, say X naught, and iteratively improve it until you arrive at a solution. So since these methods, we say that we start with an initial guess, they will not always lead you to a solutions. There has to be conditions which will be satisfied such that these methods converge to a solution, lead you to our solutions. And so there are basically most methods alongside this. I think there are so many, but so the basic ones I will look at. So here we are going to look at what is called the Jacobi method, the Jacobi scheme. Then we look at the Gauss, Seidel, and then I can just look at what S or R. Then you can go and look at this. This is what as an assignment. S or R scheme, and then you try to implement it. So this S or R schemes. So once you understand the first two and what the technique you need, then you can easily apply this technique in any of the other methods. And in fact, even in programming these methods, it's much simpler to program these methods than programming the other methods we are doing, like the Gaussian elimination method. So here, and the difference between these two schemes, as we'll see, is on updating the values. When you are using Jacobi and Gauss-Seidel, Jacobi uses the previous values to get the next one, while the Gauss-Seidel uses the latest value available. For example, if you want to find x2 and then you have the latest x1, it uses the latest x1 to get a new x2, combines them. And so it converges much faster than the Jacobi. Jacobi, even if you have the latest x1 to get x2, you still have to go and use the previous values. And so we start with the first one, which I'm saying is Jacobi iterative scheme. Or just call it the Jacobi method. So I want to explain what happens to this method, and I will illustrate just using a system of 3 equations so that we understand the procedure, and then we can now implement the procedure on any general system. So consider the system below. So I have A11 x1 plus A12 x2 plus A13 x3 is the same as B1. Then A21 x1 plus A22 x2 plus A23 x3 is the same as B2. Then A31 x1 plus A32 x2 plus A33 x3 is the same as B3. So when you want to use this method, first of all, they work well when the matrix obtained or the system is said to be diagonally dominant. is called, I think, is diagonally dominant. So basically it means what? You have the element along the main diagonal being dominant on each row. So the sum of the other two in absolute value should not be more than the what? Should not be more than the diagonal value. So in short, what I'm saying is A11, for example, here is greater than what? Is greater than A12 plus A13. So that's what their modulus. So if this happens, then it means the system is diagonally dominant. So these methods assume that way, that they work when the system is diagonally dominant. But sometimes you may have something that's not diagonally dominant, but you transform it into diagonally dominant. That means when you arrange, okay, maybe let me just write down the as a step. Maybe that will make it better. So step number 1, rearrange the system such that the resultant system has the largest element along the diagonal where possible. So I'm saying that where possible, because it's not always possible that you will tweak your system around, rearrange so that you have the diagonal elements along the main diagonal. Not always possible. But so we are saying that where possible, rearrange the system such that you are having the diagonal elements to be largest magnitude. That means here, like in this case, A11, A22, A33 in each row. Assuming along this line, A32 is dominant over this, and maybe along this line, A23 is dominant, or even not even that way, even A21 is dominant. Then I'll put this equation into 1, and then I put equation 3 into 2, such that this element becomes position 2, which is dominant. So you can keep on rearranging the system. And so let me go to procedure 2, just basically procedure 1. So assume that the system has already been rearranged such that the coefficient matrix A is diagonally dominant. So we are assuming that this already has been rearranged. That's the second procedure. So basically this procedure is just same as 1, that rearrange your system to get a diagonally dominant system where possible. As I said, it will not always be possible. Then stage 3, solve for xi in the ith equation, or in equation I. So what I mean here is, in equation 1, solve for x1. In equation 2, solve for x2. In equation 3, solve for x3. In equation 4, solve for x4. That's what we are doing. And that happens after you rearrange the system. So what do we mean? So solve in x1 equation 1. So that means I'll have x1 is the same as, if I solve for x1 here, that means I keep everything the other side, right? And so when I do this, I am just having 0 here, x1. I'm just putting 0 because there's no x1, just for for what? Just for convenience. But if you want, you can remove it. And then minus, this will be A2. What is the value of here? Yeah, this is A12. A12 x2 over A11, and then minus A13 x3 over A11, and then plus B1 over A11. Is that okay? Is it clear to everybody until this point?
Yeah.
Yeah. So you are just solving for xi in the ith equation. So in a similar manner, that x2 will be the same as minus, that is, so A21, right? I'm solving for x2 in this equation. So I'm solving for x2. So this, everything goes there, then I divide it by A22. So it will be minus A21 x1 over A22 plus x2. I'm just putting there. So I'm putting this for convenience. Minus A23 x3 over A22, and then plus B2 over A22. And then lastly, x is the same as minus A31 x1 over A33 minus A32 x2 over A33, and then plus 0 x3 plus B3 over A33. So that's our system. We have already rearranged and solved for x1. So in matrix form, the above will take the form. So I'm just taking in matrix form and vector form. So you have a vector here of x is the same as, I'll put here the j and then plus c. So call this, like you can just call this what? Just call this 1, so that if I want to refer to 1, it will be easier to label it. Where j is now this matrix. Just take the matrix of coefficient on this other side. So j will be, that is 0 A12 over A11, and then this is minus A13 over A11, and then that is negative A21 over A22, 0, negative A, is it A32 or A23? A23 over A22. Then lastly, what do we have? So we have here, this will be minus A31 over A33 minus A32 over A33, and then this is 0. So that was the easiest, that was the reason of putting the 0, so that you know that they are along the diagonal. And then C is now the new matrix of coefficients. That's B1 over A11, B2 over A22, and then B3 over A33. So basically, this method, if your matrix, you can rearrange your matrix to get a diagonal dominant matrix, then you are guaranteed of convergence. If the matrix is diagonal dominant for some equations, not all of them, but for some, you may converge. However, if that one cannot be satisfied, then you are not guaranteed of convergence. So you will not converge to a solution. And so when you look at this matrix J is called the Jacobi iteration matrix. So that's called the Jacobi iteration matrix, this J. And so when you are asked to solving this, and then somebody asks you to find the Jacobian iteration matrix, they are just looking for number 3, right? So now procedure number 4. So you have already solved for xi in the ith equation, then you get the resultant system. Start with initial guess, say x0. So it's a vector. So starting with the initial guess x0, substitute in the right hand side of system 1 to get. So remember that. So you just now start with the initial guess, then plug in x. Where this x, you put that initial guess. Then it means you get an updated value 1, which is the same as what? The j into x of 0, and then plus c. The next, substitute x1 again into 1. What do we get? We now get 2x2 is the same as what? J, and then x1, and then plus. So you see now the advantage of this method. You just keep on substituting bus, and then you move. Basically, you are doing the same procedure just repeatedly. Only get the input, use it as a, you get the output, then use it as a new input for the next step, and then get one, then you keep on updating. So continuing this way, after k steps, we obtain, what would you obtain? We obtain that x into k plus 1 is the same as the Jacobi, just j xk, and then plus c. And this is the Jacobi iteration. Why is it not highlighting? So this yellow one is now the Jacobi formula or iteration formula, where k is equal to 0, 1, 2, 3, and so on. So until this point, so if there are no questions,
Excuse me, sir.
yeah,
I have a question, just a clarification. A diagonally dominant matrix, you said it's one where the diagonal element in its respective row is larger than the sum of the other elements, or it's larger than any element. It's
the sum of all elements along that row.
Okay, thank you.
Yeah. Any other question? Because so once you do it, because we say these methods keep on going as we go. So you keep on going, you move, right? And so next is now we want to see where do we stop. Then so we say that if, for example, assume that x is a solution of our system, x is equal to b, original system, then what does it mean? It means that the limit as k approaches infinity, because we are forming a sequence of xk's. So you have x1, x2, x3, and x4. So they form a sequence. And a sequence is said to be convergent if the limit of that sequence as the indexing value goes to infinity goes to a finite value. If it goes to infinite, then the sequence is divergent. So if it goes to a finite value, that means what? That the sequence of this as xk plus 1 will be the same as what? Also, the sequence of the previous value, the predecessor of this infinity of xk, and this will be the same as what? This will be the same as the value. If it converges, then it will converge to this solution. So the sequence of these two guys will be the same as what? They will be equal. In short, so what do we mean? So you mean here that so the limit as k approaches infinity of the difference between these two values minus xk is equal to 0. So if you just taking this on the other side, so if you subtract them, it means if you subtract the two terms of a sequence and you find the limit as k goes to infinity, then you get a 0. But most cases you will never achieve this. So as I told you in the previous methods, you look at the accuracy you want. Oh, I think I'm confusing. So this one, I think I was confused with the previous class. So the Chiromo one. So something similar to this. But so you look at the accuracy you want. For example, if you want your answer correct to 2 decimal places, then you make sure that this difference between the two successive solutions are similar to the number of accuracy you want. Basically, so we stop when the set tolerance is met. And so what does it mean? So it means, for example, you are having xk plus 1 minus xk is less than a certain error you set. So if the difference between them is certain error you set, then that's now where you stop now the method. Does it is that okay? So you can now look at an example. And of course, once you understand this, then you find that it will be the same with the Gauss-Seidel. Just the difference that now when you're updating these values, we will see you update using the latest values. An example. If somebody wants, you can get an example, or you will set your own example for a different program. So this is assignment 2 starts from here. So anything I give you now, why is this one not even updating the pen? So whatever you presented was 1, and those who have not presented, they will have to present their 1. Now the other groups which you are presenting now is, which I'm writing here, this will be assignment 2. And number 1 is what? Just go and look at SOR method. Just once you know this, then you just look at SOR method. Just only get the formula of SOR method, do an example, and also write a program for the same. And that one you will see once you write a program for this other one, then the other one is easier to get a program. I think it's called successive over relaxation methods. So here an example, for example, so assume we are solving this system. So I have an example here is x1 plus x2 plus 54x3 is the same as 1, 0. And then I have somewhere having 27x1 plus 6x2 minus x3 is the same as 85. And then you have 6x1 plus 15x2 plus 2x3 is the same as 72. So that's our system. So the question is this system diagonally dominant?
No, it's not.
No.
And so is there a way we can make it diagonally dominant? What can we do to those equations so that we make them diagonally dominant?
You can just swap x3 column, you can bring it to the far left, and
Let us not swap columns. That one leave it full pivoting only.
I think we can put row 2 to row 1. We can put row 3 to row 2. Then row 1 to row 3.
Yes. So this one comes here. This one comes here, right? And this comes here. So by noticing what? If this comes to the second one, 15 becomes dominant over this, which is the diagonal element, right? If 27 goes to 1, then 27 becomes dominant, it becomes the diagonal element. If it comes here, it becomes the diagonal element. That's what you do. So basically, you are swapping the equations. And remember, by swapping the equations, you don't even change anything. The solution is just the same. You swap the equations such that the diagonal values, they become dominant in each equation. So correct. So that's what we do. It means we now have our new system, which is 27x1 plus 6x2 minus x3 is the same as 85. Good question. Why don't we swap the columns? Can somebody answer that one? But so I answer this way. If you swap the columns, you might also get something which is correct. Let me see. Maybe you might get something which is correct. I'm sure you will get something. But so remember also when you swap the columns, you have swapped variables, right? And so you need to keep track of these variables, which is something similar to full pivoting. And when you are making such a program somewhere, you are creating something unnecessary, because now you need to create a memory to track also these variables, how they are moving or how they have moved, which is something you try to minimize. It will work definitely, but in short, it's not worthy, right? Yeah. And so here it's just like what we are saying is just like now here you solve for x3 in this equation, here solve for x1, and then here solve for what? X2. That's basically what we are saying. But it's just the same as now rearranging them and then having the nice matrix. So then I'll have here 6x1 plus 15x2, then plus 2x3 is the same as 72. And then I have x1 plus x2, then plus 54. X3 is the same as what? 110. Then we said what? The next step is solve for x1 in equation 1, solve for x2 in equation 2, and x3 in equation 3. That means I'll have what? That x1 is the same as what? The same as minus 6 x2 over 27, then plus x3 over 27, then plus 85 over 27, right? And then here I have what? That x2 is the same as all the others. So minus 6x1 over 15, and then minus, this is minus 2 over 15, x3, and then plus 72 over 15. Then x3 is the same as, we'll have what? Minus x1 over 54, minus x2 over 54, and then plus 110 over 54. Is that okay? So if somebody asks you to find the Jacobi, because those are some of the questions you need to find, then the Jacobi iteration matrix is, you can just now write out this matrix. So I'll have here, this is a 0 minus 6 over 27, and then 1 over 27. And then you have here, that's negative 6 over 15. Am I writing something wrong? Do you have 2 6? Okay. Oh, yeah. So they are there. 6 over 15. And then I have 2. And then minus 2 over 15. Then lastly, we have what? This is negative 1 over 54. Negative 1 over 54. And then 0. So we will see. I said diagonal dominant, I can say this is sufficient condition for convergence. By saying sufficient, it means if it's satisfied, then you are sure of convergence. If it does not, then you may or may not converge. That's what we mean by a sufficient condition. But if we say it's necessary condition, then we mean it's if and if statement. If it fails, everything fails. If it does not fail, then everything also fails. So one of the things we check that this system will converge is by looking at something we call the spectral radius. Maybe I'll mention that later on. But so you can just keep in mind, symbol J, the spectral, this is called what? The spectral radius. So I'll mention it. You did eigenvalues, right? And so to check that a system is diagonally dominant is by getting the dominant eigenvalue. And so the dominant eigenvalue is what we call the spectral radius of a matrix. And these methods converge if the spectral radius of their corresponding matrices is less than 1 in magnitude. So the spectral radius is magnitude of the dominant eigenvalue. So it means all the eigenvalues of this should not be beyond 1, should not be less than 1. And I think so later on I'll give you a method. So it's also an iterative scheme of generating dominant eigenvalue of a matrix. Right? So that's what we will get. No, but here already you can get the Jacobi iteration matrix. That one can be done. Next, start with, so let us just start with initial value. This is equal to 0, and then x2 0 is equal to also 0, and then x3 0 is equal to 0. So I am giving you the initial conditions you start with. And then we generate. And the easiest way of generating this is just forming a table. Instead of writing them down, we form a table. So I just try to form a table, and then we will fill these values, right? So these values, so since I said this method, remember that what we said, that the Jacobi method is now given in terms of what? Xk plus 1 is the same as J xk plus C. It's just the system above. So we shall construct this table having K, right? And then I can say xk, just that's x1 k, and then x2 k, and then you have what? x3 k. I don't know, do we have space for the errors? Let me just say this is x1 k plus 1 minus x1 k. But so create also columns for also the others. Or what you can check is check here the biggest, because assume if you want your solution to be correct to 2 decimal places, then it means all of these variables, their difference will be correct 2 decimal places. So if you are checking the largest difference here of each of these ones, then you are sure that if the largest is less than 2 decimal places, then the also tomorrow is also be less than or back to 2 decimal places. But if you are not sure, just check each of this column, each of the variable. Each time you calculate, you get the difference between the current and the previous variables, the current and the previous variables. And if they satisfy your set tolerance, then you are sure you have converged. Hiyo imeenda mahali kweli ama? So we are starting with k is equal to 0. And remember, when k is equal to 0, just we have these initial conditions. This ugly guy is refusing to connect. And so here we still don't have anything. So they are just the values. And when k is equal to 1, so here the advantage of these methods, even if you have calculators, you have the same system, you are just updating what? Updating the values. And so your calculators, you can even just write, because in your calculators, you can recall the memory previous thing you calculated. So if when k is equal to 1, what is the next value? You are just plugging in here. X2 is 0 and x is 0. So what will be x1? X1 is 85/27, right? Just plug in. Just you are plugging into this system. So the initial value is the starting points. X2 0, x3 0. I only remain with this. If you go to this guy, x1 0, x3 0, then I get 72/15, which you can write in the decimal part. And then next is this 0, this 0, I get 110/54. So this is 110/54. Can you tell me? I'm just tracking only x1, but I told you check the magnitude. So the difference between this r, can you give me this in decimal? Let me try to open MATLAB here. Can you give me this in decimal? What's 85/27 minus 0?
3.15.
Is 3.15. So we just want to see, because that one, it means that the values are still far away. And then in the same manner now, we also generate here. So when k is equal to 2, what's the values? You now use these previous values, plugging into the system, and give me the current values. Tell me what is the next value? What are the next values? But that's where you are. I don't know if we can try to program this somewhere, right? Can we? Shall we try? Do you want to try it? Do you want to see how you can try this?
Yes.
Let me share this other screen. Let me first share this. But I told you one thing, even programming requires knowing. So here, I think these methods are kind of not easy, but because you are just doing the same thing. Once you get this solution, substitute back, get the next one. Substitute back, get the next one, right? So I'm now unsharing. Leave the code. Oh, why am I ending? Instead of stop sharing. So let me share this other one. So share a window. So just confirm that you can see my screen, right? Yeah. So the starting point is always defining the initial values, right? And so I am defining these values. You know you need the inputs. And so you look at your system is inputs. So even if you want to program, you will start from getting the solve system is solved for xi's. And then so when I start this, I normally write program just try to see how these things, making sure to clear the memory. You are making sure that you are not using anything stored in this. So you start by clearing so that you clear everything previously, and then you start with new things. People who do programs, sometimes you may end up getting wrong things because you are using some value which was stored previously in your program. So just to avoid that, just is what I told you. You can now you start by clearing the memory. CLC just means you are clearing this window. So if you do anything that clears this command, it clears this window. What happened? Did I close MATLAB? Oh, okay. And then after this, we now define the values. So let me just say this is x1. We said is 0, right? Then x2 is equal to 0. And then x3 is equal to 0. Then this is just we are implementing. So basically, I'm just doing this slowly, step by step, so that you understand. Let me save it, and I save it in MATLAB code. Which name do you want me to save it with? If you want, I can send you this. FEE472 Jacobi method, and then the same one can be modified. So that's now called the Jacobi method. So if I run this, then I can display the values. Then I'm just running this. You see the values go here into workspace. These are the initial values. So I want to try to create a loop. I know at this point, since you made the previous programs, you understand what a loop means. The loop means you're just repeating the same thing and then you store it as a vector. That's what it means by the loop. But so if you want to get a loop, the first thing is you get the base case of a loop, right? And so getting the best case of a loop, it means you need something to work, even besides the loop, even without the loop. And so for this to work, I can try to get x1. Maybe let me just call it x11, something like x11. And then is the same as what? Can you give me now the solution for the other one? Where we solve for x11. give me the, you remember our system after solving for the Jacobian, after solving for x1 equation and x2. That's what I want right here. Give me those values.
The first one was in decimal.
Just even fractions.
It was
Okay.
85 over 27.
No, not the answers. I mean the system, the x is equal to j plus c, jx plus c. What we solve, for example, we are having x1 is equal to minus what?
6
Minus,
over
6
27.
over 27.
so it's minus 6x2, right? So it is, this has to be product x2.
No, no. Minus 6 over 27.
6 over 27. Yeah, that's I wanted to put here the division just the same. I wanted to put the division here. Right? So that's okay, right?
Yeah.
Yeah. And then minus the second one is
Plus 1 over 27 x3.
So plus 1 multiplied by x3, then divided by 27, and then plus
85 over 27.
85 divided by 27. So let me just run this to see that it's working. You can just do it line by line. You see, I get 3.1481. Is that the correct one? If you divide 85 over 27.
Sure.
Is it the one we got with the first step?
Yes.
Yeah. And then I can just copy this line and then paste it here. But I want this to be x12. Or yeah, x. So it means the second solution. So let me just say x21. Now, can you give me this value? So equation for x2, what do we have? Tell me equation for x2.
It's negative 6 over 15.
Negative 6 over 15. But it is what? It's x1, right?
Yes, that's x1.
x1. And
For
then
x3,
yeah.
it's 2 over 15.
So here, did I make, yeah, this was x2 and x3. So this is x3 is 2 over 15. So that is 2 divided by 15. And then plus
72 over 15.
That's 72 over 15. That's 72 over 15. And then lastly, sorry, negative 2 over 15. Okay, let me, I'll change it. So that's minus 2 over 15. And then I can put here equation for this is, I can just call this x31. Then it's the same as what? So read to me the equation for x31.
Minus 1 over 54.
So that's minus 1. Next.
54.
Is it minus? Yeah. Next is what?
Minus 1 over 54 x2.
Again, right?
Yeah, x2.
So that's minus 1 over, that is x2. And then this is 54.
110 over 54.
110 over 54. So once you make this program to work, it means you have these values. And what these methods do basically here, what the system does is, instead of getting these values manually and then plug in here, and then you repeat this process manually. So you want to tell your program that now, can you repeat this process, right? And so to repeat it, I can get a loop for I is equal to 1 until n. N is just my number of what? The length of this loop. How many steps do I want? For now, I've not set the error first. I just want to go maybe 5 iterations. I can say maybe n, I want 5 iterations, right? And then anyway you do, you end. Right? let me indent. So anytime you start a loop, you end. That's what will happen by a loop, right? You end that loop. And what you do, you can now pre-assign the vectors. Or you pre-assigning, it means I'm defining a zero vector of all these inputs. And so this zero vector, I can just call it maybe, let me say, call it x. So just to differentiate with the previous one, is zeros of 1, n, nn. So zeros 1, let me just run this. Let me put this 3 so that something you can see quickly what I mean. I know this might give you an error, so don't worry if you get an error in these other ones. Yeah, I know this one. I wrote double zeros. So these others might give you an error. Let me comment on them. Let me suppress them first. I just want you to, what I want you to see is this vector. So the zero vector just initializes the vector of the length you want, if there are 0, 0, zeros. If you want a row vector, then you put here, and then you change this to be 1. So for those of you who do programming, initializing creates already a memory of the same length. So it is easier for the program to replace something in the memory than to create a new one, a new memory for every time you go. And so I just want to do this. I want to pre-assign all this, all of them into, just initialize their vectors. So it is x2, and then this is what? This is now x3. So you see I pre-assigned all of them are 0, zeros. And so when I change n, I'll just also change everything. And what do we need? It means the first values of this should be exactly this, the values you define here, right? So we now create a loop. And remember, if I is equal to 1, meaning if you are starting the initial values, then what does it mean? X1, for example, I will be the same as x1. If you are it means I'm just telling it that the initial conditions are what I'm given. Then x2 into bracket I will be the same as x2, and then I can just copy the same thing here. Now, if there's something I do here and you don't understand, just let me know. That is x3 is the same as x3, because so I want to tell it that if these values are the initial conditions, then you pre-assign them this, and anytime you start an else, you end. So if you start an if, you end. If you start an else, you end. So I want to end, but I want to change this now. So x1 is just basically this x1 and then I. Let me first change this and then change this. This will be now 2, and then change this. This will be now 3, right? And then so here I use the previous values. So I just copy anything of this. To get the next value, you are using the previous values. So these people who are now calling me. So this is x2, right? So I have to use x2 at the previous time point. So it is I minus 1. So all these other ones will be the values at I minus 1. So that is I minus 1. And so this will be xx1 at I minus 1. And then this will be xx3 at I minus 1. Then you can do the same here. So that will be xx1 at I minus 1. Then here you'll have what? X2 at what? I minus 1. So if you recall what I wrote in the Jacobi method, let me put here in a comment, right? So we said that x into bracket, that is k, plus 1 is equal to xk. I can just say the same as saying that xa is the same as what? J into xk minus 1, and then plus c. This is what I've implemented, basically. Because instead of going with the previous value that xk is equal to the value at xk, it means I can say that the current value is put in from the previous value. Does that make sense? Kuna mtu mwenye aelewe? Ama kuna mwenye ako na swali? So if I run this, then you can check this. You see how the x1s are moving, and then you see how x2s are moving, and then you can see here how x3s are moving. Or let me see. Let me try to combine these matrices. My x is equal to, then this is what? And that is xx1. They are supposed to be commas, right? So this is xx2, then comma xx3. And then I can do this. I can say this display. Will this display all these things? Let me see, comma this, comma this. Maybe this is x1 solution, and then this is x2 solution. So we got already everything. I'm just looking for if you want to display. Let me first see if this one will work. Okay, maybe it doesn't. And then I can now do this display. Now this is x. Okay. So I wrote this with capital. So you see these are now how the solutions work. But so sometimes I don't know how can I move this to. Do I have some display somewhere, the wrong display? X1 solution, X2 solution, and then X3 solutions. Let me see. Can I try to move it somewhere? Let me see this. Okay, it moves. And then I'm just so that you can see how these ones align. But basically we have a solution. If I want to go, how many iterations do you need? Even 10, right? Then you see 10 iterations. Can you even tell me the solution until now? What is the solution? So you can also, you basically see so kuna mwenye ako na swali? Hello. Yeah. Anybody with a question?
Yes, so you said if you are able to get the Jacobian, then that will just tell us that it will converge without even going through the process of.
Not if you get the J and you get the spectral radius and show that the spectral radius is less than 1, that means, in fact, I just wrote this in system form, but I could have written this in matrix form. Basically means I can just extract here outside the J, and then I find the eigenvalue just by saying ig in MATLAB. It will give you an eigenvalue. and then you see, do you have the one of dominant magnitude or the largest, and then you display that one. But so this is converging because you can see that you are going to a solution, right? They are almost becoming equivalent or same, but this is just the implementation, the basic one. The other one I can do is now, after this, is now you put the condition that if you converge, then you stop, right? Then you can tell it that if you find these conditions, then you stop basically. But so here, what can we do? Do you want to find errors, right? You want to calculate errors. So I can say maybe error 1. I can just also initialize. Let me just copy these values. So and then so that error 1 will be for the first one, and then this error 2 will be for the second one, and then this will be for the third one. And so once I do that, then I can come here. If you are at the first one, you don't have error, then you can say error 1 I is equal to, let me just say x1, right? Or initially, if you want, initialize, just give it a very large error, so such that if you are timing something, then I can say just to E1, or maybe just anything. Then I can do the same to this, and then to this. So this will be error 2. Meaning, when you start this program and you want error to converge, start by giving it the first error to be large one. If you give it a small, it will stop to read that it has finished. And otherwise, once you do this, then you can now say error 1 I, right? This is I is equal to what? The difference between the successive values. So it is the value at I minus the value at I minus 1. But we are only interested in absolute values. So I can say here absolute values of these errors. And then you can do the same to the other variables. So just copy this, and then you paste it here. So that is error 2, and then that will be 2, that will be 2, that will be 3, that will be 3, and then that will be 3. So I want to, yeah. Oh yeah, it's thank you. It's supposed to be error 3. So here the errors will be calculated. I can also just try to display these errors, right? So I'm just combining all these matrices. So this will be error 1, and then this will be error 2, and then here will be error 3. And so I just want to display each one next to its error. So this is what? So that's x1. Let me just call it x1 error. And then I can do this. So that is x3 error. And so what I need here is what? Okay, so maybe I could have done this. And then I put this here. And then I put this other guy here. Let me see what comes out. Okay, so it's not able to arrange everything the column wise. But so you see, this is your x1, and this is the error for x1. You see now errors are equal to 5 decimal places, right? This is maybe, let me format short so that we only display the few values. So you see the format short. So these values, you see the errors are almost going to 0. So this is error for x1, this is error for x2, and then this error for x3. So it means this is your solution. So you can go back, finish up that program, and then see that you get this solution. You can, if you want now, you can just set this very high, but you ask it to stop, right? So you just do this, and then you say, if once you can get these errors, then I can say what can we define our what tolerance do we need? Tolerance, for example, you want what, maybe 1 e minus 6, or maybe something like, we want accurate 6 decimal places. So you are now conditioning it. You can use this and you put if statement, or somebody can use a while loop, whichever works. While loop also, there are conditions. And then I say, if I say if error 1, that is error I, right, is less than tolerance, and then, and so because since we want to check all the errors, we need to check that all of them have tolerance. So this is error 2, and this is what, this is error 3, and then this is, then break end. So if it will check if this is satisfied, then it breaks, otherwise it continues. First of all, let me just comment on this line. I wanted to shift control R. Control. This is different from what I'm used to. So I can let me just comment on this line, right? And then even maybe put here 20 iterations. So you see that this thing will just proceed until 20. So you see it displays how many? 20. If you also, you can even put here the K so that you count here the I's. But if I keep the same everything there, but I only activate this part, I only activate this part, then what will happen? Let us just see what happens. You see, it goes to this how many iterations? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It still did everything. It did not stop. And but I don't know why this ugly guys decided not to stop. So you can just put here format long G, so it writes in the scientific notation. But so it's basically trying, is not stopping. However, this has stopped. But did I put break? If error is less than tolerance and this is less than tolerance, then it has to break. I don't know why it's not breaking, but it has to break and then stop the computation. And then you end. But basically, this is at least you now have idea of how you program this. And then you can now program this. You can use whichever you want. So any other question?
Yes, I have a question in regards to the assignment, the SOR methods. Could you kindly expound on what you expect us to do?
Basically, just do the same example. SOR method is just also part of the method of like the example of Jacobi. So I just want you to write down the formula for the SOR like we have for the Jacobi, and then apply it on an example, right? And also implement it. Even another assignment is also this Jacobi method. You have to implement it also in a program. Just make a program that calculates the Jacobi method and does everything. And in that method, just also write down this matrix, and you find the dominant eigenvalue. Just use the ig function, and then you check the dominant one, and then you comment. So they also I want you just to get the formula and know how to use it. You don't have to read the whole. You can read the whole theory to understand. But what I just want you to is you get the formula and write it down and use that formula to do an example. Make sense?
Yes, it's not coding. It's we do a manual on paper, an exam.
On paper and coding, you implement all these methods. You'll implement all of them, right?
Yes, it's noted.
Yeah. And coding Gauss-Seidel is the easiest. It's just the same as this. Gauss. So I can just mention this in the next class. I just look at Gauss-Seidel, and this the only difference between the Gauss-Seidel and the Jacobi is Jacobi method, as you are seeing here, it's using everywhere the updated values, right? No, not the previous values. However, the Gauss-Seidel uses the current value update. So like you see, for example, in this part, once I've done here x1, it means I have the latest x1. So in the Gauss-Seidel, I will go and use that latest value x1 instead of the previous one. So that's what happens. For x3, I still have the previous value, so I don't update anything. If you go to the x3 equation, for the Gauss-Seidel, I have x1 already updated, right? And I have x2 already updated. That's basically the Gauss-Seidel. And then you may see that these zeros will move up. You see that you'll have many zeros. It converges as twice as fast as, you see, I've already implemented it. So that's only the difference between Gauss-Seidel and Jacobi. It goes through the whole process, but you use the latest value available to you. That's the value you use. Hii iko sawa? But I will illustrate it just also in the next class, just to see the formula, because we need to get the Gauss-Seidel matrix, and then you can get the spectral radius. So that one I will do in the next class. So unless there is a question, I prefer to. So if you copied this, it's okay. You can just, even if you are using even Python, you are using anything. These programs, once you know what happens, then you can move away from one language to another, and then you can use. Even this, you can write it even also in a different format, and then you use the J matrix, and then just multiply J by X. So you can still write it in the format in the same way you want, in a different way, a different something, right? Any question? If no question, is there anybody who wants to present? Okay. So I was wondering, this was presenting the zeros because of so it was, the method is basically stopping here. The system was stopping here, but it just presents these zeros because I was wondering why it's not stopping. So this zero is because of the pre-assigning the matrix. It's just displaying the whole matrix, but it basically stopped from until here. Maybe I don't know if what I can say, display I from 1, I think from 1 to I think this one maybe will display only until the, and now it has the problem is that if you do this, then it arranges in terms of what? The column matrix. Let me see. Okay, so I'm the one who messed up. So only the column, and then the columns are varying. Yeah, that one. Yep. So this is the difference. That if I comment on this line, right? I don't know. I forgot the shortcut for commenting on this. I only know the Windows. If I comment on this line, you want to. So I want you just to appreciate this. So count the number of lines you have the case. So here the case are only until 1, 2, 3, 4, 5, and 6. If I remove that line, you see it runs everything throughout the whole loop. However, if you put this condition, even if you put the others to be 1,000, mostly people put these other values, big one, then you don't care. Even if you put here 1,000, it will stop exactly once it gets the value. You see, it just stops exactly once they're satisfied. So that's the if condition. You can put an if condition, or some people use the while loop. While this error is still not less than this, proceed. Otherwise, stop. Is anybody wants to present?
Yes, group 17. Ready to present.
Okay, so the rest of the other people, you are free to leave. Any other person? So otherwise, I can listen to at least maybe 2 or 3 presentations. So that's group 17.